No, it don't! No, it don't!
In grade, I believe it was grade 10, when your teacher taught you how to graph y, it was grade 11, equals to x squared. And the way your teacher taught you how to graph this, I guarantee you, was simply using something called table of values. Back in the days, x, y, you chose -1, 0, 1, probably -2 here, and 2. You create a table of values and so on and so on. And what you really end up with is a graph that looks something like this. You plot points. Problem with this method is it's actually a guessing game. The reason why is you put -2. -2 is 4, 1, 0, 1, 4. So you put points here, points here. The problem with this method really is this is actually a guessing game. The reason why is, how do you know that this line in the middle is accurate? How do you know the shape is this? How do you know that the shape couldn't be something like this? You know? How do you know the shape isn't like that? I match all the points, but how do you know the shape isn't like that? So that's what we're going to use now. We're going to use calculus to prove that the shape is actually something called parabola. And this is how we're going to use calculus. I'm going to teach you about calculus and using something called increase and decrease. Increase versus decrease. Very, very simple concept. Now, an increase, by definition, really goes up. Just basic definition. Decrease, by definition, is it goes down. Just basic definition. If I were to give you a simple graph like this, y equals to x squared. I'm going to ask you for something called my critical point. Okay, so let's look at my critical point. Find your critical point. Critical point. Take a minute and find your critical point right now, please. Go. Sorry, what's going on? DEC, December. This is increase versus December. Any other questions? Y prime equals to 2x. So would you agree my critical point is 0? Now this, remember, a point of either max or min. We don't know yet. Or min. So here's what we're going to do. We're going to find out my something called regions of increase versus decrease. Regions of increase and decrease. Here's how you're going to find the regions. A graph is increasing if, so let's write this down. A graph is increasing if f prime of x is greater than 0. Very basic sense. So which means the slope of the tangent has a positive. It is decreasing if, notice I'm using the derivative function, not the original function, is less than 0. So I have two sides. I want to know where is my prime greater than 0 and where is it less than 0. So what I'm going to do, I'm going to create a little number line. You probably were exposed to this before in grade 11, where we're going to test my regions. Here is something called your critical point. I want you to put your critical point here for me, please. This is number line. My critical point is 0. So I'm going to write in 0. That's the first thing. Because that's the point where your graph is not increasing or decreasing. I have two regions. The yellow side and the blue side. When I chop it up, I chopped it up into two regions. So what we're going to do now is, I want you to choose any number to the left of 0. Doesn't matter what number you like. And we're going to sub it into my derivative equation to see if it's increase or decrease. Let's choose. Now, Kieran, give me a number to the left of 0 for me. Go. -1. So what I'm going to do is, if I want to test if it's increase or decrease, I'm going to choose my derivative equation. So I go y prime equals to 2x. See, I'm working with the derivative. So now this becomes equals to 2 times -1. I just chose any random point here. And I chose -1. Plug it in. And when I plug it in, I get -2. So this is a negative value. And according to my equation, if it's decreasing if f prime is less than 0. So we're going to call this a decrease. Personally, when I like to write a decrease, I draw a little line going down like that. Okay, that shows decrease. Some people like to draw it, but I like to draw a little arrow going down like that. I want you to do the next region you own. I'm going to pause it. So if I tested region number here, but Joanna, what number did you use? 3. So for Joanna uses 3, I go y prime equals to 2 times 3, which gives you 6. So you notice this is positive. So we call this as an increase. So to show increase, I'm going to draw an arrow pointing up. So I kind of get an idea of what the graph is doing. It's dropping this way, and then this is going to be increase. So we call this, if it goes from low to high, this is called a local min, because it's dipping right there. Notice I'm not using the word absolute. The reason why, because I never give you boundaries to work with. So right here, locally, is the min. It could be absolute, but we don't know yet. That is called increase versus decrease. Try this question. G of x equals to x plus 2 sine x. I'm going to ask you in 2 parts. A, find regions of increase / decrease. To help you out, this will be from 0, x, to 2 pi. B, identify local max / min. That's all I'm going to give you to do. I'm going to give you about 10 minutes to try on your own. I'm going to walk around. I'm going to help you out. Have fun. The key is getting the derivative. So the derivative, g prime of x, equals to 1 plus 2 cos x. Agree? I want to set this equal to 0 because I want to know my critical point. Cos x equals to -1 over 2. From 0 to 2 pi. I'll give you a hint. Special triangles. Go. What quadrant are you in? I got up to here. Here is my triangle. Now, some of you must know the answer is easily pi by 4, yada, yada, yada. Anything by 4 is not correct because wrong special triangle. So this is -1. This is 2. What the heck is this side? Root 3. Therefore, we need angles now. What is this key angle right here? In terms of radians, pi by 3. So this is pi by 3, but that's not the answer. See, everyone thinks that's the answer. That's my reference angle. That's not the answer. So x equals to 2 pi by 3 is one of them, which is 4 pi by 3. Because from here to here is 1 theta. But remember, these are not my answers because I'm asking for regions of increase and decrease because I want to know what the graph is looking like at those points. So this is known as my CP, my critical point. Once I have my critical point, let's draw your region. Number line. Put in your number line and test your regions for me. Go. Here's 2 pi by 3. Now some of you say, so can I use decimals at this point? The answer, yeah, you can use decimals if you want, if you're so afraid of whatever. Again, change your calculator to radians mode. You should be in radians mode, guys, not degrees. Okay. Choose a number to the left of 2 pi by 3. If I were you, I'm going to choose the easiest one possible, which is? Nope, easier. Easier. 0. If I were you, I'd choose the easiest one possible, and which happens to be 0. So now, notice I'm going to sub into my derivative formula, not the original. Here's where people get mixed up all the time. It's my derivative formula I'm going to use. So this is going to be g prime x equals to 1 plus 2 cos 0. Cos of 0 is 1. Well, 1 times 2 is 2. So your answer is, where is? Wait, give me 1 second. G prime x equals to 3, I believe. So now, notice 3 is positive, so therefore we call this an increase. And to show an increase, I like to show pictorially, so I'm going to use the little arrow showing up. Go ahead, do the next one, Yon. Some of you must know, what number should I use between 2 pi by 3 and 4 pi by 3? There's a really easy number. Pi. Because pi is right here. Hi, question. Hi. No, these are critical points. Yeah, this is number line. Okay. This is not a graph, this is just a number line to test the regions. So now I want you to go ahead and test out pi and tell me about the shape of the graph and do the next one on your own. So I'm going to pause it. The next part, if you test out this region, Ryan says, Miss No, this is actually a decrease. Okay. Go ahead, test it out. If you don't have a decrease, holla. Okay, I'm going to come around, I'm going to pause it. Should be a graph that increases. So if I look at this graph, notice it looks something like this. Doot, doot, doot. That's the general shape of the graph. Because, so therefore, there's my increase and there's my decrease. This is a decrease. Now what they're going to ask you is, find the max and min. From my graph, you should be able to tell me where the max is and where the min is. So right off the bat, Karn, where's my max? Yeah.
0 and 2 pi.
No. 2 pi by 3 is correct. See this point right here? Because it tips out, see? Goes up, 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 up. So all of a sudden it hits here, and it drops down. So right off the bat, local max, let's write this down. Local max occurs at 2 pi by 3. At 2 pi by 3. Very nice. Local min. 4 pi by 3. Local min. Because if I look at the graph, see? It goes down and goes up. Therefore, my lowest point has to be at 4 pi by 3. 4 pi by 3. So therefore, I just know the general shape of the graph. Is that the right graph? It's almost accurate. Not yet. See, I didn't need to use point testing. I just used calculus to solve this question. The next problem is, so how do you know if the graph is shaped like this versus a squiggly line like that? And go squiggly line down and squiggly line up. Oh, we do now. We're going to use calculus to prove that it's actually a straight line. Okay? Because what I have is squiggly like this. Nope. I'm going to show you a calculus way of doing this. So now, the question is, how to tell concavity. Concavity. Concavity, really, this is called a shape. Okay? I'm going to show you something called concave up. Concave up. Concave up really means the graph kind of curves up. Now that's like a concave, concavity up. Concave down. Concave down, the graph kind of curves down. So let's draw a parabola for me, please. And this is where I'll end my lesson for today. That's it. Pretty short lesson today. My parabola, y equals to x squared. Would you agree every one of you were taught to draw a parabola like that? Every one of you. Okay. So I'm going to teach you the difference between concavity versus increase and decrease right now. Few key things. I'm going to highlight this shape. From here to here, we have something called a decrease. Very simple. It's a decrease. From here to here, we have something called an increase. But overall, the graph has a concave up shape. Concave up shape. Okay? Overall, the graph has this concave up shape. Very simple concept. But if I were to give you this question, draw the graph up. Okay, right there. I'm going to highlight a few key pieces for you. This part is increase right here. Okay? Increase. But if I look at the shape, would you agree somewhere up to probably here, this yellow piece is concave down? Just based on the graph. I can't show you mathematically yet. I'm going to show you in a second. This blue piece right here is concave up, because that's what the shape is. Concave up. So concave up and concave down has nothing to do with increase and decrease. You can have increase and concave down. Question is, how do you find concavity? Do you find concavity? We call this concavity. And this is what you need. To find to figure out your concavity, you need an inflection point. Inflection point. We're going to call this IP. Ip Man. Have you seen the movie Ip Man before? No one? Oh, 2, 3! My Chinese brothers, welcome. Ip Man is actually a good Chinese movie. How you never seen it? It's a actually later. So I call this Ip Man. You can need, and the formula for Ip Man is this: is f double prime of x. So what we're gonna do is we want to find my inflection point. Generally occurs when your second derivative equals to 0. My first derivative is called critical point. My second derivative is called inflection point. I got where I go. If f double prime of x is greater than 0, we call that concave up. Very simple concept. If f double prime of x is less than 0, we call that concave down. Your question is this. At 0 is that inflection point, or we call that my Ip Man point. F y equals to x to the power 4 minus 4x cubed. I'm going to ask you lots of things for this one. A, I want to know my increase, decrease regions. B, local max / min. C, I want to know my Ipman point. D, concavity. Concavity. When I mention concavity regions, I want to know where's it concave up, where's it concave down. You can't put all this in a graph yet. This just shows you the general shape of the graph. Have fun. If you guys need a hint, I need to find first derivative. Right off the bat, here's my first derivative. I need to know my critical points because I can't do anything yet without my critical points. I set it to 0, 4x cubed minus 12x squared. So I'm just going to know, what do you do now? Well, guys, when in doubt, F it out. So factor it out. 4x squared, that gives you x minus 3. Right off the bat, you should know your critical points. That's very, very simple. Say, Nick, what's your critical points? 3 and 0, correct. So these are my points of either max or min. That's why we call it critical points. I don't know yet. So what I like to do is I like to draw a number line. 0 and 3. Go test your regions right now for max and min. It's a lot of work, but is the work that hard? No, it's not really. Oh, that's where people make the mistakes. This is where you gotta be careful. Where do you put it in to test the points? Whoa, 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 whoa. Do you put in the derivative? That's where mistakes lie. It's F prime. So when superhero day comes up, guys, you too can dress like Ip Man. I should dress up like Ip Man. And my symbol will be an F double prime. Okay. Test your regions. I'm going to test in -1. If I test -1, the graph should be going down, I believe. Okay. And the beauty about this is this. There's actually a nice trend. If one goes down, the other tends to go up. Oh, you got down also? Oh, sorry. I should test my. I was trying to use shortcut. So let's try to use the 1. That's going to actually go down also. Down? Hi. Then, this, I believe, will go up. So this is actually a down, down, up graph. Some of you may say, what the heck is a down, down, up graph? So, now, in order for you to understand that and explain how this goes down, down, up, we need to know something called my inflection point. Because from the inflection point, maybe it gives me a little hint of how the graph looks like. To do the inflection point, I no longer work with my first derivative. I need my second derivative. Why? Double prime. So you can actually do this now on your own. So that gives you 12x squared minus 24x. Go ahead, solve for x. Ip Man. Figure out my IP point yet? X equals to 0 and 2. Now these points, I should clarify what IP points are. These are points possible. I'm going to write down this down. Possible points for IP. I'll explain to you what IP points really are in a second for IP. Okay? And I'm going to give you this true definition of what IP is. Star this one, star. An inflection point is a point where the graph changes concavity. Changes concavity. Sounds weird. What it does means is this: concave up, then all of a sudden goes to concave down, or concave down to concave up. To explain this, you're going to need to test your regions, and I'll explain to you how. Put in 0 and put in 2, and test your regions right now for me, please. 0, 2. Go. So right off the bat, I'm going to test. Notice I'm going to use the second derivative this time. So I go 12 times -1 squared minus 24 times -1. If you did it correctly, you should get something called concave up. To show concavity up, I'm going to do a little u to show that the shape looks like that on that side. Okay. Then I'm going to do the next point between 0 and 2. Go ahead and do the next point for concavity, please. The graph goes down, I believe. And then it goes up. So right off the bat, I want to highlight these points. Notice where this changes. 0, 2. It changes points. So these are called my inflection points, IP, because it changes concavity here and here. So how does the graph look like? I'm going to show you why and how later once I put it together. But for now, let's draw the quick sketch. I'm going to show you, demonstrate how this works. I know that 0 is a key point. The graph goes down to 0, but notice it's concave up to the left of 0. So I'm going to draw a concave up. Concave up looks something like that. Right there. See? And it goes down to the left of 0. From 0 to 3, it also goes down. But somewhere along here, we're going to call it 2. Because that's my next point. It's going to be somewhere here. That's going to be concave down. So I want you to go ahead and predict how the graph looks like from here to here. And that has to concave down. Okay. I'm going to draw, so concave down would look something like that. That's concave down. Then, at 3, it goes down till it hits 3. So let's have a 3 point right here. 3, we'll call it 3 somewhere down here. But at 3, notice what happens up to 2? It's concave up. So I want you to predict the last piece on your own. Go. So from here onward, it has to be concave up. So let's do it in red this time. So watch my last piece. It's going to be concave up. And after 3, it goes up. What I just drew is a perfect graph without using any points from a table of values. Okay? Perfect concavity. Concavity up, down, up. I'm going to do some highlighting just to make highlight for you. Hi. No, that's for tomorrow. You're not ready yet. This is now I just teach you what concavity really means. See? Concave up. Because that's why it looks like it here. Concave down. That's why it looks like concave down here. And finally, concave up in this last piece.
So what proved it doesn't have more like...
You can't have any more curves. You can't twist it sideways because it destroys the concavity. That's the reason why. So now, this is concave up. That is a perfect shape you can possibly draw. You can't have concavity within concavity, no. Okay? So you can't, if it does, then it has to have a breakage right here, inflection point right there. Your work! That's it for today.